Crack an egg on the edge of a bowl. Now try to uncrack it. Pour the yolk and the white back through the shell, seal the crack, and have a whole egg again. You can't. Nobody can. Not with any tool, not with any amount of patience. And here's the part that should genuinely bother you. Physics has no law that says you can't. Not one. Every fundamental equation governing every particle in that egg works exactly as well backward in time as forward. So if the laws don't forbid the reverse, why does it never, ever happen? Stay with me. By the end of this video, you'll know the actual answer, not its obvious, but the specific, working, still slightly mysterious physics behind it, including evidence from as recently as 2010 and 2012 that most explainers never mention. Here's how strange this actually is once you sit with it. Film literally anything governed only by the basic mechanical laws. 2 billiard balls colliding, a pendulum swinging, a planet orbiting a star, and play the footage backward. Nothing in the physics of that reversed footage is broken. A physicist, watching both versions, forward and backward, examining only the forces and motions, genuinely cannot tell you which one is the real direction, because both obey the equations equally well. But show anyone, physicist or not, a video of a cracked egg reassembling itself, or a puddle of spilled coffee leaping back into the cup, and they'll laugh within half a second. Somewhere between 2 billiard balls and 1 cracked egg, an asymmetry sneaks into the picture that isn't sitting anywhere in the fundamental equations themselves. Finding exactly where that asymmetry comes from is the actual subject of this video, and it took physics the better part of a century and a half to nail down, with new pieces still being added as recently as this decade. You probably assume there's a law of physics, some rule about atoms, that only lets time run one direction. There isn't. Gravity, electromagnetism, the strong nuclear force, run any of them backward in a simulation, and you get a perfectly valid, perfectly legal universe. The one-way street you experience every day, cause before effect, egg before scramble, isn't written into the rulebook of physics. It's hiding somewhere else entirely. Here's the shape of the actual investigation we're about to run, so you know where you're headed. First, we rule out the obvious suspect. Maybe some fundamental force secretly does forbid running backward, and we just haven't noticed. Second, once that suspect is cleared, we go looking for the asymmetry in a completely different place, not in any single law, but in how many ways things can be arranged. Third, we follow that counting argument all the way back to the beginning of everything, because if disorder always increases going forward, it has to have been decreasing going backward, and that trail leads somewhere genuinely strange. Each step builds on the last, so stay with the order. Let's start with the most reasonable guess, because it's wrong in an interesting way, not a stupid way. Take the law of gravity. Film a planet orbiting a star, then play the recording backward. The planet still traces a perfect ellipse, still sweeps out equal areas in equal times. Every rule of orbital motion is satisfied, exactly as well running in reverse. A physicist watching the reversed footage has no way to tell it apart from the original. The same is true of electromagnetism. Reverse a video of 2 magnets interacting, and every field, every force, still checks out. It's true of the strong nuclear force holding atomic nuclei together. Reverse time in the equations, and the physics doesn't complain. Now, you might object. Some systems don't look symmetric at all. They look wild, unpredictable, chaotic. Take a double pendulum, a simple arm hinged to another simple arm. Its motion looks nothing like a clean ellipse. It whips and tumbles in a way that seems to have no order to it whatsoever. Surely that's where the arrow of time hides. It isn't, and the reason is worth sitting with because it corrects a common confusion between 2 completely different ideas: unpredictability and time asymmetry. Chaos means a system is so sensitive to its starting conditions that tiny differences explode into wildly different outcomes. That's what makes long-term weather forecasting hard, and what makes a double pendulum look random, even though it's governed by the same clean, deterministic equations as the orbiting planet. But run a chaotic system's motion backward frame by frame, and it is exactly as valid a solution to the equations as running it forward. Chaos scrambles your ability to predict the future from imperfect knowledge of the present. It does not, on its own, scramble the forward-backward symmetry of the underlying law. That distinction matters here because it rules out a tempting shortcut, The arrow of time is not simply complexity or unpredictability wearing a disguise. It's something else, and we're about to find out what. There is exactly one narrow exception, discovered experimentally in 1964, and it's worth naming because almost nobody outside physics has heard of it. At Brookhaven National Laboratory, James Cronin and Val Fitch were studying a subatomic particle called the neutral kaon. The expectation, based on a symmetry physicists call CP symmetry, charge conjugation combined with parity, essentially swap every particle for its antiparticle and reflect the universe in a mirror, and the physics should look the same, was that certain kaon decays simply shouldn't happen. Cronin and Fitch found that, rarely, about one time in 500, they happened anyway. That tiny, stubborn violation of CP symmetry, confirmed and refined over the following decades, and worth a Nobel Prize in 1980, implies, through a deep theorem connecting charge, parity, and time called the CPT theorem, that time reversal symmetry itself must be very slightly broken too, somewhere in the weak nuclear force. For almost 50 years after Cronin and Fitch's discovery, that CP violation was the closest thing physics had to direct evidence of time asymmetry at the fundamental level, but it was indirect, inferred through the CPT theorem rather than measured directly. That changed in 2012. A team working with the BaBar detector at the SLAC National Accelerator Laboratory, using nearly 500 million pairs of particles called B mesons and their antiparticles, managed something physicists had wanted for decades: a direct measurement of time reversal violation itself, not inferred from CP violation but observed directly, by comparing the rate at which one quantum state transformed into another against the rate of the reverse transformation. The two rates were different. Time reversal symmetry really is broken, measurably, in this one narrow corner of particle physics. Here's why neither of these results actually solves our egg problem. They're astonishingly small, narrowly confined to rare interactions of the weak nuclear force in exotic, short-lived particles. They have essentially nothing to do with the eggs, cups, or coffee cups you interact with every day. Your scrambled egg isn't staying scrambled because of kaon or B meson physics. Something else, something bigger, statistical, and much stranger, is doing almost all of the work. There's an everyday clue hiding in plain sight that points toward where the real answer lives, and you felt it with your own hands. Friction. Rub your palms together, and they warm up. Press a car's brakes, and they heat until they glow. In both cases, organized motion, your hands sliding in one clean direction, a wheel spinning in one clean direction, gets converted into something that is technically still motion, but now it's the disorganized, random jiggling of countless individual atoms which you experience simply as heat. Nobody has ever pressed a warm brake pad and watched it spontaneously cool itself down while launching the car back up to speed, converting that random atomic jiggling back into one clean, organized motion. That conversion only ever runs one way. Order into heat, never heat back into order, for free. It's the exact same one-way street as the egg, just wearing the costume of your morning commute instead of your kitchen counter. So let's go back to the egg and actually count, the way a physicist would. A whole egg has exactly one way to be a whole egg. Yolk here, white there, shell intact, everything in its design place. A cracked, scrambled egg has an almost incomprehensibly larger number of ways to be a mess. Every possible splatter pattern, every possible mixing of yolk and white, every possible distribution of shell fragments counts as a scrambled egg. There's one way to be whole. There are, for all practical purposes, infinitely many ways to be broken. This number of ways, the number of microscopic arrangements that all look like the same macroscopic thing, is what physicists call entropy. It isn't a mysterious force pushing things toward mess. It's just counting. When your egg cracks, it doesn't move from order to chaos, because chaos is somehow attractive. It moves there because there are catastrophically more chaotic arrangements available than orderly ones, and every random jostle of atoms is far more likely to land you in one of the many messy arrangements than in the one single tidy one. The second law of thermodynamics is just this counting argument stated formally. Left alone, a closed system's entropy never decreases on average. Not cannot decrease under any circumstance in the mathematics. It absolutely could. if every atom happened to jostle in exactly the right coordinated way. It's just so staggeringly unlikely, given the sheer number of atoms in an actual egg, that the reverse has never been observed in the history of anyone watching anything. Here's an experiment worth actually running with a friend, because it makes the scale visceral. Pour a small splash of milk into a cup of black coffee. Watch it swirl, curl, spread, and within seconds, uniformly mix. Now try, by stirring, swirling, blowing on it, anything you like, to get the milk to separate back out into a single clean blob, floating on top of pure black coffee. You will fail every single time. For the same reason, the egg won't uncrack. The mixed state has astronomically more available microscopic arrangements than the separated one, and nothing you do with a spoon can beat those odds. Try one more, because it drives the point home from a completely different angle. Build a sandcastle at the beach, as detailed and careful as you like. Walk away for an hour. When you come back, wind and passing feet and the occasional rogue wave have very likely knocked bits of it down, never built it up into something more elaborate. Nobody has ever returned to a sandcastle to find it more intricate than they left it, spontaneously improved by the random buffeting of wind and sand. That's not because sand wants to fall down. It's because there is exactly one way to arrange that sand into your specific castle shape, and a near infinite number of ways to arrange it into a shapeless heap, so any random disturbance overwhelmingly tends to knock you toward one of the many heap-shaped outcomes and away from the one castle-shaped outcome. Here's a version of the same asymmetry that has nothing to do with heat or mixing at all, which is worth including precisely because it shows how far this pattern reaches. Drop a stone into a still pond, and ripples spread outward in neat, expanding circles. You have never once, in your entire life, seen the reverse. A pond spontaneously organizing its surface into circles that converge inward from every direction and eject a stone upward into your hand. Nothing in the wave equation governing that ripple forbids the inward converging version. Mathematically, it's an equally valid solution. But producing it would require coordinating an entire pond's edge in perfect synchrony to focus its motion on one exact point at one exact instant, an arrangement so specific among all the ways a pond's surface could possibly be moving that it never happens by accident. Physicists sometimes call this the radiative arrow of time, and it's the same statistical logic as the egg in the sandcastle, wearing a different costume. Outgoing, spreading disorder is common. Incoming, coordinated order is vanishingly rare. Ice melting into water works the same way, for the same underlying reason, on a scale you handle every single day without thinking about it. A single ice cube has its water molecules locked into one comparatively small set of ordered, crystalline arrangements. Once it melts, those same molecules can jostle into an almost incomprehensibly larger number of loose, liquid arrangements that still look, from the outside, like a glass of water. You have never watched a glass of room-temperature water spontaneously grow an ice cube out of nowhere on your kitchen counter, and it isn't because there's a law against it. It's because, out of all the ways those molecules' energy could randomly redistribute itself, enough of it coincidentally concentrates in one small region to freeze it solid, is such an infinitesimally small slice of the possibilities that you could wait many times the current age of the universe and still not see it happen. Physicists sometimes explain this to students with a version of Maxwell's demon, a hypothetical tiny being that watches molecules and sorts fast ones from slow ones, seemingly creating order from chaos for free. For decades, this was purely a thought experiment, dating back to physicist James Clerk Maxwell in the 1870s. But here's a piece of genuinely new physics that most arrow of time explainers never mention, because it's recent and slightly technical. In November 2010, a team led by Shoichi Toyabe published an experiment in the journal Nature Physics that built something close to a real Maxwell's demon. Using a microscopic bead and real-time feedback based on information about the bead's random thermal motion, they demonstrated that you actually can convert information itself into usable physical work, lifting the bead against a force, essentially climbing a tiny staircase, using only knowledge of which way it happened to jiggle. This didn't break the second law. It confirmed something predicted decades earlier by physicist Leo Szilard in 1929. Information has a genuine, measurable thermodynamic cost and value. Acquiring, storing, and erasing information about a system's random motion is itself a physical process, bound by the same entropy accounting as everything else. The demon doesn't get free order, it pays for every bit of order it creates with the thermodynamic cost of the information it used to create it. That's worth sitting with for a second. Information is not just a metaphor here. It is, provably, a physical quantity with a real thermodynamic price tag, one of the more genuinely mind-expanding results in 20th and 21st century physics, and one almost never mentioned in the "why can't you unscramble an egg" explainer you've probably already seen. This is also the point where it's worth naming something most explainers blur together, because keeping it precise actually makes the whole picture click. Entropy always increases, and disorder always increases are not quite the same sentence, even though people use them interchangeably. Entropy is the precise, countable thing, the number of microscopic arrangements consistent with what you can observe from the outside. Disorder is just the everyday word we reach for because, in cases like a cracked egg or a melted ice cube, more arrangements happen to look messier to a human eye. But the counting is what's doing the actual work in the mathematics, not any built-in preference for messiness. That's why physicists trust the second law completely as a statement about probabilities and arrangements, while still treating disorder as a helpful metaphor rather than the literal mechanism. Keep that distinction in your back pocket, because it's exactly what separates a real physics explanation from the looser, vaguer version of this story you've probably already heard somewhere else. Here's where most explanations stop, satisfied, and where the actually interesting question starts. If entropy only goes up, if disorder is simply more statistically likely and always wins in the long run, then the past, by the same logic, must have been more ordered than the present. Your egg was whole yesterday. The universe, billions of years ago, must have been in an even lower entropy state than it is now, and lower still before that. Follow that logic all the way back, and you land on an extraordinary claim. The early universe, right after the Big Bang, must have been in an almost unimaginably ordered, low entropy state. This idea that the universe's low entropy past isn't derived from any deeper physical law, but has to be added as an extra assumption about the initial conditions of the cosmos, is sometimes called the past hypothesis. It sounds almost too simple to be a real scientific puzzle, but it is one of the genuinely open questions in modern cosmology, and here's why it's stranger than it first sounds. Before we go further, it helps to know just how much entropy the universe is capable of holding, because the numbers here are almost impossible to hold in your head. Physicists Jacob Bekenstein and Stephen Hawking showed, independently, in the 1970s, that black holes carry entropy proportional to the surface area of their event horizon, not their volume, which is already strange, implying that a black hole's information capacity is written on its surface like a cosmic hologram, not stored in its interior. A single black hole with the mass of our Sun carries an entropy roughly 100 million times larger than the entropy of the Sun itself in its current form. Supermassive black holes, the kind sitting at the centers of galaxies, dwarf that further still. By current estimates, the entropy locked up in the supermassive black holes of the observable universe absolutely dominates the total entropy budget of everything else combined. Every star, every planet, every person, every scrambled egg put together is a rounding error next to it. That number matters here because it tells you just how far the universe still has left to fall, entropy-wise, and therefore just how staggeringly ordered, how staggeringly far from that eventual state the early universe must have been to have any of that increase still ahead of it. The universe isn't just a bit more ordered in the past. It started at a level of order so extreme, relative to where it's heading, that physicists still don't have full agreement on how to even properly define, let alone explain, just how special that starting point really was. You might think a hot, dense, uniform early universe, the standard picture of the instant after the Big Bang, sounds disordered, not ordered, the way a well-shuffled gas of particles usually is. This is the part that surprises almost everyone the first time they hear it properly explained. Gravity flips this intuition on its head. For an ordinary gas, uniform and spread out is the high entropy, shuffled state. But for a system dominated by gravity, uniform and spread out is actually the low entropy, highly ordered state. Gravity always wants to clump matter together into dense knots like stars and black holes, and it's the clumped, structured universe of galaxies and black holes we have today that represents the high entropy outcome gravity has been steadily working toward. The smooth, uniform early universe was, in a precise, countable sense, staggeringly improbable, a needle in a haystack of possible starting conditions for a universe. This is where the physicist Roger Penrose made a specific, falsifiable proposal called the Weyl curvature hypothesis, named for a mathematical quantity that measures a particular kind of gravitational field distortion, the sort of tidal stretching and gravitational wave-like curvature that has nothing to do with ordinary matter density. Penrose's proposal is that this Weyl curvature was essentially zero at the very beginning of the universe, an extremely specific, extremely restrictive condition, and that its steady growth since then, as matter clumped into stars, galaxies, and black holes, is the actual physical account of the universe's gravitational entropy increasing over cosmic history. It's a real, technical hypothesis about the actual geometry of space-time at the Big Bang, not a philosophical handwave. And it remains, honestly, unconfirmed and actively discussed, not a settled textbook fact. Why does a proposal like this matter so much to physicists if it's still unconfirmed? Because it converts a vague, hand-wavy phrase, the early universe was special, into something you can, in principle, actually check. A precise geometric quantity that should have been at or near zero, that should grow in a specific, trackable way as cosmic structure forms. And that should connect, mathematically, to the same entropy bookkeeping used everywhere else in this video. That's the difference between a scientific hypothesis and a philosophical intuition. Not certainty, but the property of being pinned down precisely enough that evidence could, in principle, support or undermine it. Whether Penrose's specific version turns out to be the right account, or whether some other geometric or quantum gravitational mechanism eventually replaces it, the past hypothesis itself, that a low entropy early condition is required, is treated by working physicists as close to inescapable given everything we currently know, even while its ultimate origin remains genuinely open. I want to be honest with you about where the frontier actually is, because this is exactly the kind of claim that gets oversold into false certainty. Physicists broadly agree that the early universe had extraordinarily low entropy, and that this fact, not any law of physics, is the ultimate root of why your egg, your memory, your aging body, all point in the same forward direction. What physicists do not agree on is why the early universe had that specific, special condition. Some, following threads from Penrose and others, look for a deeper physical or geometric reason. Others, echoing an idea physicist Richard Feynman himself raised in his own 1965 lecture on this exact topic, wonder whether it's simply a brute fact about our particular universe, a boundary condition physics has to take as given, the same way you take the rules of a chessboard as given before you ask why any particular game unfolded the way it did. This is also the reason the entropy story doesn't end with today's galaxies and stars. It points forward as much as it points backward. If order has been running down from an extraordinarily special starting point ever since the Big Bang, the same logic that demands a special past also demands a specific future. A cosmos that eventually settles into the most probable, most spread out, most disordered arrangement statistics allows, once every star has burned out and every black hole has slowly evaporated over timescales that dwarf the current age of the universe many times over. That end state has a name of its own, and it's a story big enough that it deserves its own dedicated video later in this series, rather than a rushed paragraph here. For now, the point is narrower and, honestly, more useful. The same counting argument that explains your breakfast also frames the entire life story of the universe, beginning to end, and you're living inside the middle chapter of it. There's one more thread here, because it's the single strongest argument against an idea you might already be forming. Maybe the ordered universe we see is just a lucky accident, a random fluctuation out of a much longer-lived, disordered universe, the same way it's technically possible, if astronomically unlikely, for your scrambled egg to unscramble itself given enough time. This idea has a name, the fluctuation hypothesis, and physicists, including Feynman himself in that same 1965 lecture, have a specific, devastating objection to it sometimes now called the Boltzmann Brain problem, after the physicist Ludwig Boltzmann, who first wrestled with versions of this puzzle in the 1890s. If the order we observe really were just a rare statistical fluctuation in an otherwise disordered universe, then the overwhelmingly most probable way for that fluctuation to happen is the smallest possible fluctuation that could produce a single momentary conscious observer, not an entire ordered galaxy full of consistent history, stars, and other minds. A random fluctuation vastly prefers, in a strict probability sense, to produce one lone brain floating in a sea of chaos, complete with false memories of a coherent past, rather than an entire self-consistent, genuinely ordered universe stretching billions of light years in every direction with a real history behind it. Since we do observe a large, consistent, richly detailed ordered universe, not a lone brain with fabricated memories, the fluctuation hypothesis, taken seriously, actually argues against itself. The far simpler, far more probable explanation, given everything we actually observe, is that the universe really did begin in a genuinely low entropy state, not that we're a statistically freak accident dreaming the whole thing. There's one more version of this arrow worth naming explicitly, because it's the one that actually feels personal, the one you experience directly rather than infer from an egg or a distant galaxy. You remember yesterday. You do not remember tomorrow. Physicists sometimes call this the psychological arrow of time, and the genuinely interesting claim, going back to observations Feynman himself made about memory in his own lectures, is that this isn't a separate mystery from the entropy story. It's the same mechanism, running through your own skull. Forming a memory is a physical process. Something in your neurons has to change state and stay changed. New connections strengthen, proteins get synthesized, physical structure gets laid down. Every one of those physical changes, like every physical change anywhere, has to be paid for thermodynamically, and that payment necessarily increases entropy somewhere in the process, whether in your brain's own metabolism or in the surrounding environment absorbing the heat your neurons give off doing the work. A memory, in other words, is a small local pocket of increased order, a photograph, in effect, bought at the price of increased disorder elsewhere, exactly like every other example in this video. That's why you can have a physical trace of the past sitting in your head right now, but no equivalent physical trace of the future. Creating that trace is a one-way thermodynamic transaction, and the books can only be balanced by entropy going up, never down. You don't remember tomorrow for the same reason your egg won't uncrack. The physical process that would have to happen to write that memory runs in exactly the direction the second law allows, and not the other one. This is part of why the honest complication from Rovelli, coming up next, matters so much rather than being a footnote. If even your subjective sense of now and the flow of time is entangled with a physical, entropy-driven process happening in your own brain, then untangling what time really is from what a limited memory-forming observer like you experiences turns out to be a genuinely hard problem, not a solved one dressed up to look hard. One honest complication before the reframe, because I'd rather you hear it from me than feel misled later. Not every physicist agrees that entropy is even the right lens for the deepest question of why time flows at all. The physicist Carlo Rovelli, in his 2018 book The Order of Time, argues that much of what feels like a universal, flowing now is itself an illusion created by our limited, coarse-grained perspective as macroscopic observers, that at the deepest level described by quantum gravity, a single, universal direction of time may not be a fundamental feature of reality at all, only an emergent one tied to the particular blurry way beings like us interact with the world. This isn't a rejection of anything in this video. Entropy increase is still real, still measured, still the reason your egg won't uncrack. It's a reminder that why does entropy itself increase from a special starting point, and is a flowing, universal time, even a fundamental feature of reality, are two different open questions, stacked on top of each other, and honest physics communication should let you see both layers rather than pretending the deeper one has already been settled. Here's the reframe. You've probably heard time's arrow comes from entropy, stated as if that fully answers the question. It doesn't, not on its own. Entropy increasing explains why disorder is statistically favored going forward from any given starting point. It does not, by itself, explain why there was ever a starting point ordered enough to have anywhere to fall from. The real answer, the one most explainers skip because it's less tidy, time has a direction because the universe began in an extraordinarily special, low-entropy state, for reasons physics can describe mathematically but cannot yet fully explain, and everything you experience as the past being fixed and the future being open, every memory, every cause coming before its effect, every egg you'll never uncrack, is downstream of that one deep, still, slightly mysterious fact about the beginning of everything. What do you actually do with this? Here's the honest, non-mystical version. Every time you notice something breaking down, a relationship drifting apart, a project sliding into chaos without maintenance, your own habits decaying without upkeep, you're watching the exact same statistical logic play out at human scale. Order takes continuous, active work to maintain, because there are always vastly more ways to be disordered than ordered, and entropy doesn't pause for good intentions. That's not a metaphor stretched to fit. It's the identical mathematics from the egg, scaled up. The practical takeaway isn't fatalism. It's that maintaining order anywhere, a marriage, a garden, a body, a company, is never a one-time act. It's a continuous payment against a universe that is, at every level, statistically pulling the other way. Here's a concrete version of that continuous payment idea, rather than leaving it abstract. Think about learning a language, or maintaining a fitness routine, or keeping a friendship active across distance. None of these decay because some malicious force is attacking them. They decay because staying fluent, staying fit, staying close are each exactly one narrow target out of an enormous number of ways things could drift. And drifting requires no effort at all, while holding the target requires deliberate, repeated, ongoing work, exactly like Bekenstein and Hawking's black holes, slowly radiating away order over cosmic time, exactly like the Toyabe demon paying an information cost for every bit of local order it creates. The universe was never going to maintain your Spanish vocabulary or your friendships for you. Every keeping in touch text you send, every hour of practice you put in, is a tiny, local, temporary victory against the same statistical current running through everything else in this video. There's a second, subtler takeaway too, and it's about how you evaluate claims about the past. Because the second law only runs one direction reliably, the present genuinely does encode real, recoverable information about the past. That's why geologists can date rock layers, why historians can cross-reference documents, why your own memories, however imperfect, are actually anchored to real prior events rather than pure invention. The same statistical logic that keeps your egg from uncracking is what makes the past happened and left traces a physically grounded claim, not just a comforting assumption. When someone tells you evidence points to a particular history, they're leaning, usually without knowing it, on exactly the physics in this video. There's a third, quieter implication too, and it's the one that actually changes how you might treat other people day to day. If every act of remembering, every photograph, every diary entry, every scar is a small local increase in order bought against a background of rising disorder, then evidence of the past is never free. Someone kept that photograph. Someone wrote that entry. Someone's body did the metabolic work of forming that memory and holding onto it against every statistical pressure trying to erase it. Treating recorded history, personal or collective, as something that took real, ongoing effort to preserve, rather than something that simply persists on its own, is a small shift in perspective with a large practical consequence. It's a reason to actually value the people and institutions that do the unglamorous work of keeping records, because the universe is not on their side by default. Every archive, every family album, every carefully maintained scientific instrument log is a tiny, local rebellion against the same overwhelming statistical tide this whole video has been describing. Every conversation you've ever had, every memory you can access, every plan you're allowed to make about tomorrow but never about yesterday, all of it rides on top of one single cosmic fact. Roughly 13.8 billion years ago, the universe started in a state so improbably ordered that physicists are still trying to fully explain why. You are not separate from that fact. You are one of its consequences. The reason you can remember this morning and not next Tuesday. The reason regret points backward and hope points forward. The reason your cracked egg will never reassemble no matter how long you wait. It's all one thread, running all the way back to the first improbable moment anything existed at all. Think about what that actually means the next time you feel the small, ordinary grief of watching something end. A conversation, a season, a chapter of your life, closing the way it does. Once, in one direction, never looping back exactly the way it was. That feeling isn't separate from physics. It's the same one-way arrow, felt from the inside, that keeps your coffee from unmixing and your egg from reassembling. You are not fighting a personal, private unfairness when things don't reverse. You're standing inside the single largest pattern in the entire universe, one that was already running for billions of years before you existed, and will keep running for a very long time after. There's something almost consoling in that. If you let it land, your grief at irreversibility is, quite literally, cosmic in scale. You're not alone in it. Everything is. And there's a second, quieter feeling worth naming before we close, one that usually gets crowded out by the grief, gratitude, of a very specific kind. You exist, at all, as a conscious being capable of noticing any of this, only because the universe happened to start in a state ordered enough to still have almost 14 billion years of usable structure left to spend on building stars, planets, chemistry, and eventually you. That's not a guarantee written anywhere. It's a debt the early universe paid forward, one you're spending down every single day you're alive, the same way every organized thing in this video spends down the order it was given. Noticing that isn't morbid. It's closer to noticing, really noticing, that the light from a star you're looking at took years to reach you. Except this time the star is the improbable beginning of everything, and the light is you. When you first heard the laws of physics don't actually forbid time from running backward, did that feel unsettling? Or did it feel like the universe finally admitting something you'd always half suspected? Tell me, before this video, did you think entropy was a force pushing things toward chaos? Or did you already know it was just statistics? No, wrong answer. If you want the physics taken all the way to the real frontier, not stopped at the tidy textbook answer, that's what the Physics Storyteller exists to do. Subscribe to the Physics Storyteller and keep going past where most explainers stop. This is part 1 of 3 on entropy and time. Next, we ask the stranger question. This one opens up. If the past determined the present through this one-way arrow, does that mean the past, in some real physical sense, still exists somewhere? That's next, on the Physics Storyteller. The egg on your counter this morning is not just breakfast. It's a small, local piece of evidence about the first moment of the universe. Tell someone that tonight. Watch their face.